Thank you for organizing this wonderful seminar series, and thank you for the introduction. And today I'm going to share with people here about some of the older and newer work from my research on learning algorithms for solving combinatorial optimization problems, right? And especially combinatorial optimization problem over graphs. So it is quite in some sense, broad class of problems. It doesn't matter what kind of domain you're working with. It doesn't matter if it's a social network, artificial system, or biological network system. You will invariably encounter networks where node can be a user in social network, edge can be interaction between people. A node can be a protein, and edge can be protein interaction, things like this. Or node could be a node in the electrical grid, and then the edge can be some kind of transmission line between different transformers in a electrical grid. So very often when you are trying to work with this graph data, you will try to solve some kind of combinatorial optimization, trying to optimize some selection of people or placement of sensor, things like this. Okay. So there are many combinatorial optimization problems you can define over graphs, but today I'm going to use a very simple running examples to talk about combinatorial optimization problem over the graphs. So it will be this very simple minimum one discover problem. So already it's simple, but it has application in a, like advertisement in social network and selection of sensor to place in some kind of sensor network, things like this. Okay. So the problem is very simple. You have such a network. What you want to do is you want to select a set of nodes. If these particular nodes are being selected, we're going to assign a variable y equal to 1 to this variable. If it's not selected, then it's going to be 0. So what we want to do is to select as few number of nodes as possible, but we want to make sure that each one is edge in the network. At least one end of the edge is being selected. So this constraint is enforcing that for two ends of the edge, at least one end is going to be selected. Okay, so it's such a simple problem, but it's an NP-hard problem. So you have to go for some kind of approximation algorithm or heuristic algorithm to get a good solution. And people have looked into this problem and designed many algorithms for it. And one particularly simple algorithm and with the approximation guarantee is this two approximation guarantee algorithm, which is going to select edges in some sense, two ends of an edge or two nodes at a time based on the degree of these nodes. So it's a iterative algorithm. What you're going to do is you're going to take the graph as the inputs. You're going to measure essentially the degree of each node, and then you're going to sum together the degree of the two ends of the edge. Okay, the two nodes which is connecting to two ends of the edge. So you can think about the scaling function. There's a scaling function given the current graph for each one is node. It's exactly the sum over the number of incident edges, okay, or number of neighbors which hasn't been selected, okay, and then the score of a particular edge is going to be sum of the scores of the two ends. So you can think about that this particular scaling function is defined by human expert. It can actually be computed with some kind of message passing scheme as well. You can think about that if I want to score a particular node, I will ask the neighbors of the node to send in messages. I'm going to count the number of messages which is containing this label 0, and then use that as my score. So this here is an expert designed kind of a scoring function which can be computed by this simple message passing scheme. And although it's simple, it's a two approximation algorithm, right? But these many algorithms which are designed previously, in some sense, is designed in a traditional paradigm. So it's a traditional or classical paradigm in the sense that you try to focus a lot on the worst case performance of the algorithm. For some of the easy problem, you can actually design polynomial time algorithm for it. For NP-hard problem, like what we just encountered, minimum well discovered problem, and then you have to design either heuristic or approximation algorithm for it. Put it simply, suppose you have a space of problem instances X. So you pick a particular problem instance from the space of problem instances. And your algorithm is to produce a solution, and there's a way to measure the quality of solution using this loss function. You try to find, in some sense, an algorithm. In some sense, traditional algorithm design is to try to find an algorithm, the parameters of the algorithm, which trying to perform well, or the loss is small, even for the hardest instance, okay, the worst case. But actually, in nowadays, combinatorial optimization problems are solved in many industry settings. For instance, in Amazon, they're solving maybe some of the challenge salesman problem every day. In some online social platform, they're solving this type minimum order cover problem every day. So it's not just a single problem which is being solved, but you actually have a family of problems which are being solved again and again, right? So this family of combinatorial optimization problem actually follows on distributions. They have, each instance is actually going to have some similarity in some sense. For instance, suppose this minimum value cover problem we encountered earlier is going to be an online social advertising problem. You are trying to pick the node or the users in the social network to advertise for something. Hopefully, this user is going to help you spread, you know, the particular information about particular product. You suppose you want to do this every day, right? Every day you can think about the social network is going to be an instance for your combinatorial optimization problem. And each one is network in different day are going to be different because sometimes some people are logged in, some people are not logged in, some new user joined, some old user dropped. The network are more or less the same. The number of users are more or less the same for each day, but the connectivity is going to change a bit across the day, and the node will also change a bit. So although it's not exactly the same problem you're solving, the combinatorial optimization you're solving is not exactly the same, but they share some similarities. So in some sense, giving you a family of problem instances, what you hope for is you can actually exploit and leverage some structure of the distribution, trying to find some algorithm, okay? Or the parameters of algorithm, which can actually perform well in this class of problems. And then and you measure the performance of the algorithm in terms of expectation, okay? On average, you want the algorithm to produce good result, okay? And being able to do it fast, things like this, okay? So many of the traditional classical algorithm design, they try to design algorithm which you possibly have some probable guarantee on the worst case performance. But very often in a current industry setting, these combinatorial optimization problems are solved again and again. What you want to do is to leverage the data, maybe machine learning algorithm, to learn some algorithms which can perform well on these class of problems, or on average, you can perform well, okay? So this is, this second setting is the setting we're going to focus on. And since we're minimizing the loss function like this and leveraging the family of problem instances that allow us to use learning, and some, especially some of the deep learning approach and differentiable approach to learn some kind of combinatorial optimization problems, okay? So actually, recently, one thing has been very popular in the space of graph combinatorial optimization problem is something called graph neural nets. I'm just going to give you one slide, very quick introduction of graph neural net, just in case you haven't encountered it before. So graph neural net is going to be some deep learning approach or model defined over graph structures. And what this graph neural net is trying to do is to learn a vector representation for each one is node in the graph. And then this vector representation is going to be produced in an iterative fashion. So you're going to initialize, for instance, each one is node by vector representation. And then you're going to iteratively update the embedding, the vector representation. For instance, if I want to update the embedding for this particular node, hi or I node, then I will request the neighbors of this node I to pass in the messages, or pass in the current embedding of the neighbors. And I'm going to perform one, after I sum together, pull together all these messages from the neighbors, I'm going to perform some kind of neural net updates and produce the updated embedding for this node I. So I'm going to do this same message pass and update for each one is node. And once I finish one sweep of every node, I'm going to start the next round of update. So I can actually iterate the message passing process for t times, and then until you get some kind of a vector representation for each one is node. So at that point, then you can actually use this vector representation for the node to define some kind of a scoring function for the node. and to determine whether I should select this node into the solution set, for instance, for this minimal discover problem. So this graph neural net is trying to, in some sense, capture, the neighborhood information around a particular node I. And then the number of iterations you run for this graph neural net is sort of equivalent to the size of the neighborhood, or how many hops away you want to look at the information among this graph. And then since the message passing operator in this graph neural net is parameterized by some neural net. So here, these neural nets with parameter W1, W2 is parameterized by W1, W2. So you're not going to fix this neural net parameter, right? So it's going to be some parameter which you can learn based on a family of problem instances, okay? So I have explained this hand design, expert design, two approximation algorithm for minimal cover before, right, in the previous slide. And it is a very simple message passing scheme where you ask the neighbor to pass in the message and do a simple count of the number of neighbors. And that's in some sense, a special case of this formula. You can imagine if I can tune this W1, W2, I can actually recover the simple counts as a special case. So when you actually get a space of a family of problem instances and trying to learn this parameter in this message passing operator W1, W2, it's equivalent to search over the space of graph algorithms. You can think about when you're optimizing the parameter in these graph neural nets, you're searching over the space of graph algorithms. So this graph neural net has been intensively used nowadays in the space of trying to learn some combinatorial optimization algorithm for graphs. Okay, so I'm going to talk about three aspects in the remainder of the slides. One aspect is to actually forming this graph algorithm learning problem as a reinforcement learning problem, and then use reinforcement learning to learn these parameters in this graph neural net to solve combinatorial optimization. The second kind of aspect I'm going to talk about is what is the limitation of this graph neural net-based approach when you're trying to parameterize it as some policy for solving graph combinatorial optimization problem? How do we actually make the search space of this graph neural net bigger such that you can find potentially more powerful algorithm? The third aspect I'm going to talk about is once you have learned a nice policy for solving graph combinatorial optimization problem, can we understand what kind of feature this learned algorithm is using for making the decisions? So what is the structure or in the graph which make this learned algorithm decide whether I should select this node rather than the other node? Let's just first look into the first aspects. How do you actually frame the graph algorithm, especially a sequential kind of algorithm, as a Markov decision process, and learn with the reinforcement learning for graph algorithms? So, actually, I'm going to just look back into this running example. So of minimal cover problem, where you're trying to minimize the number of selected nodes subject to the constraint that at least one end of the node is being selected, right? So what it means is actually you can map this objective function into the reward function in reinforcement learning. So every time you select a particular node, you are going to be penalized because you want to select a small number of nodes as possible. In some sense, in this case, the reward is -1 or the loss is 1, okay? So this is a very simple greedy sequential algorithm. You can think about in this particular expert design, the greedy algorithm, you are using the degree of each node to score a particular node, right? That's like an action value function you define in reinforcement learning. Given the current graph S, so you will have some kind of way to score individual node, and then by selecting that node, it gives you some kind of what is the expected reward kind of produced by the selection of that particular node. And then in the second step, when you're using this particular scoring function to select the node, it's like taking a greedy action in the reinforcement learning setting. right? Once you select a particular node, and in these two approximation, you're going to remove actually the selected node, and that changes the graph. That changes the states of the Markov decision process. And then you're going to take the modify the graph and go through this action value function again and determine the next node to select, and then select it, and you change the graph. You keep going until all the nodes, all the edges in this particular graph has been covered, as at least one end being selected. Okay, so if you map this the optimization problem into this reinforcement setting or Markov decision process setting, then it becomes a little bit natural to think about, what if I replace this action value function by something more expressive, by a function, right? Instead of using a expert designed a fixed function, I'm going to parameterize this function. I'm going to learn this function. So in this particular case, we're going to use graph neural net to parameterize this action value function and use reinforcement to learn it. So the overall rough flow of these, in some sense, the learning process is also simple. You have not just one training graph, but you have a family of training graphs, right? Because you want to solve a family of problems. Suppose you have already collected this family of graph problem instances you want to solve. And then you have this parameterized graph neural nets, right? Suppose you have already a fixed parameter of this graph neural net. For each one of these graph, you run this graph neural net neural parameterized method passing operator. It's going to produce you a set of node embedding. It's a vector for each one of this node. And once you have that, you can actually use that vector embedding in this case to define the action value function. Right? Given the current graph and given the embedding of a particular node, you're able to define this action value function by introducing some additional parameters such as theta1, theta2, theta3 here. Once you have this action value function, and then you can just use this reward, of -1 to use it like DQN. You try to learn these parameters in this action value function together with the parameters in this graph neural net, which produces the embedding. So you can imagine that after this reinforcement learning process, you will learn a policy, right? Essentially, if you take the greedy action according to the action value function, that's going to be a policy. So you can actually, because this action value function is parameterized, you can apply this action value function to a new graph, right? If you have a new test graph, you want to also use your policy to solve this combinatorial optimization, you can do that, right? Using this learned graph neural net together with these theta1, theta2, theta3, defining this action value function. And that's what we did in this 2017 paper for learning combinatorial optimization over graph. In that paper is the first one for using graph neural net to parameterize this type of selection policy. So we tried this approach in several combinatorial optimization problems, including minimum cover, challenge salesman, and the max car, and some other algorithms. I'm going to just use minimum cover and show you a video or animation of the differences between the learned algorithm and some of the expert design algorithms, including the node greedy selection and edge greedy selection, these two approximations. So here is the sort of animation and comparison. I will just play this video first. On the left side is going to be the algorithm learned by graph neural net. On the middle is going to be this greedy algorithm, which are going to pick the highest degree node, and then this one is edge greedy. Is going to pick the edge where the two ends of the edge has the highest total sum of degree. So every time the node is being picked, you're going to remove that node and the corresponding incident edges from the graph, and you work with the remaining graph. If your algorithm is running faster in terms of number of steps, then it's going to clear out the graph faster, okay? Because every time you select some node, the graph is going to be, removing some node and edges. So if you solve the problem faster, then the corresponding, the graph is going to be clear faster. So the graph looks slightly different at the beginning because of the visualization, but they are exactly the same graph. We can look at this video again. So what's interesting is this algorithm learned by graph neural net initially, it doesn't seem to be the fastest algorithm because this node greedy algorithm seems to be able to clear the graph very quickly, right? So it looks like it's almost clean, it's almost done. But actually, when the algorithm proceeds near the end of the algorithm, the graph neural net is able to actually catch up and finish the problem faster. So when you observe it more carefully, what you will see is because this greedy-based node greedy or edge greedy, they're actually too greedy in some sense. It's very myopic. It doesn't looking into the potential long-term effects of being greedy, okay? And in this node greedy, the node selected at the beginning it has a very high degree. And the selection of this node will result the graph being fragmented into lots of small components. These small components are not connected at all. Then near the end of the algorithm is forced to selecting at least one node from each component, and which actually slow down the algorithm near the end. But this graph neural net based approach is able to select node which somehow balance a bit between the degree of the node. The node selected is relatively high degree, but it has been picked in a way that it makes sure as the graph is still connected. It's not going to fragment the graph into small components. And then that actually allows the algorithm to reserve the potential to select the node which is able to remove lots of edges, even near the ends of the running of the algorithm. So you're learning some kind of new algorithm which balances between node greedy and the connectivity of the graph. It's very interesting, exciting to look at these data animations to see that actually this learning-based approach allows you to discover some new algorithms which are actually performing better than these, two approximation, which has a guarantee, okay? And especially if you have a family of problems, the learning-based approach seems to be able to produce, able to learn some algorithms which has much better approximation ratio comparing to those expert design algorithms, okay? So we have actually, as I mentioned, the experiment on traveling salesman problem, and also on max cut, and later on minimum dominant set, and even set cover problem. And we find that across this range of problems, using learning, this reinforcement learning based approach, you are able to learn some algorithm which actually perform better than some of the expert design algorithm, right? And so this is good so far. Actually, so we are also looking into what will be the limitation of this learning-based approach. So graph neural net is intrinsically local, right? It's like a passing message locally. And if you just run graph neural net for t hops, it's only looking at the neighborhood of t hops. How do we're making it more expressive? How do we make it look at the global information and potentially learn even better algorithms search over larger space of graph algorithm? So then we actually look at the approaches to make it more expressive. To understand the limitations of the graph neural net based kind of policy for parameterizing graph algorithms, so we have to look at something called distributed local algorithm. There, it's related to distributed computation over graphs, and actually some result from the community of distributed local algorithm design, which can be used to understand limitation of graph neural nets. So earlier I've been talking about sequential algorithms, right? Especially this sequential algorithm where the selection policy is learned by graph neural net. Essentially, the algorithm, the node is selected sequentially. Once you select the node, the incident edge are being removed, and you select the next node, and some of the edges are being removed, and then you do this sequential until all the edges are being removed. So in the distributed local algorithm, it's something like this, and the node selection are performed simultaneously, right? So you have some policy which probably gives you some probability of a node should be selected into the solution set, and then you're going to make a decision simultaneously, and then you're going to select a certain node and declare that's my solution. And the question is, how do you actually perform this, compute this probability of being selected? And the probability selected is also going to compute in message passing fashion, but they are produced in a parallel fashion and distributed fashion. So using some of the results from this distributed local algorithm community, you're going to show both the expressiveness of GNN you can express distributed local algorithm. Final step of this algorithm, for instance, you can show that you can express some graph isomorphism test algorithm such as Westphal-Lemon algorithm. If you just run this graph isomorphism kind of test algorithm for t-hops, you can show the graph neural net can actually express that algorithm. But its graph neural net is also limited in some sense that you only run t-hops. And then with t-hops, you can even show that the best kind of distributed local algorithm can achieve certain, approximation ratio no better than something in some of these examples. You can imagine there will be some cases where the solution, the better solution, really needs global information about the graph, and graph neural net is not able to capture it. So besides the representation kind of power of the graph neural net, it's limited when you don't have global information. The computation of graph neural net is also limited by how much information you can look at. If you want to look at a larger neighborhood in your graph, you increase your t, then that means that your forward computation when you pass the message is going to grow bigger, exponential in the average degree of the node in the graph, and then the number of hops you run. And then it also creates difficulty when you try to optimize the parameter in graph neural net, because you need to pass the message backward, right? And that's also going to be computation intensive. Maybe you also have a gradient kind of decay problem, diminishing problem like what you will see in recurrent neural nets. So this limitation actually prevents people to, run graph neural net for many hops, especially on large graphs. And people often find that even you increase the number of hops, graph neural net doesn't seem to be helpful, okay, to capture more information. So that prompts us to think about how will we be able to, equip the graph neural net with some ability to capture global information, and such that you can learn better graph combinatorial optimization algorithm or search over a more expressive space of graph algorithms. So based on these kind of questions, or inspired by such questions, we look at some augmentation schemes for the graph. Okay, we're going to change the graph to something different. In this case, you will see that we're going to augment the node and edges of the graph with some additional information, such that graph neural net can capture the global information. So actually, the idea is inspired by some algorithm from theoretic computer science literature. So in this particular case, we are inspired by near linear time algorithm for solving large-scale Laplacian system. So we can think about this graph Laplacian is pretty much the adjacency matrix of the graph, by the way, something like identity minus the adjacency matrix. And you try to solve, treat it as a matrix, and you try to find the solution of linear system, where X is the solution you're trying to find, B is a vector of the right-hand side of the linear system. So if you just treat it as general linear system, then the best algorithm you can have is like performing the matrix inversion here in times B, and it's going to be out of n is the number of nodes in the graph, n to the power 2.373. But Keller et al. Has designed a near linear algorithm. This algorithm has two steps. The first step, this algorithm is going to approximate, or it's not approximate, it's find something called the low stretch spanning tree of the graph. So what it means is that, for instance, the original graph is the grid structure, and the spanning tree are going to be this, this graph with thicker edges. Okay, the spanning tree. So in the original graph, there are many loops, right? Because the grid, because you have trying to approximate this graph with a tree, many of the loops are destroyed. For instance, originally I can go from one node here to the other node just by one hop, but now because I approximate the original graph by a spanning tree, I have to travel a longer distance to reach the other node. So these low stretch spanning tree make sure that the distance of each pair of node is not going to increase by a lot, even you approximate the original graph by a tree structure. So this algorithm is going to first, approximate the original graph with something called low stretch spanning tree, and then you're going to solve this linear system. You're going to, you're going to follow the graph Laplacian based on this spanning tree, and solve this linear system using this spanning tree version of graph Laplacian. So because the tree structure, actually the solution can be done in linear time very efficiently. Okay. And once you have the solution based on the tree structure, you're going to refine locally the solution. So you're going to actually trying to close up, trying to add back some of the edges which is missing in the spanning tree, and trying to refine the solution in this local loop. Okay, so it's a little bit while some kind of message passing like operation. So it's actually very similar to graph neural net. Okay. So that algorithm actually inspires us to do something similar for graph neural. Essentially, we're going to take the original graph where you try to solve the combinatorial optimization problem and approximate it by some kind of tree structure and obtain some solution using the tree in linear time. And then we're going to use the solution based on the tree structure to augment the original graph and then run graph neural net on top of it. That's the sort of the high level idea. So just to make it more specific, here is a very toy example where you have a graph structure here. You're going to approximate the graph using some tree, right? So here, the kind of grain edge are those edges which are not in the spanning tree, and you are approximating the original graph by the spanning tree. Then, for instance, if you try to solve a minimum width cover problem, then you can solve it, solve that problem in the spanning tree. You can do it in near linear time in this spanning tree. Once you have obtained a solution of minimum width cover problem in this spanning tree, some of the nodes are selected, right? Some of the nodes are not selected. So you can think about you can augment each node in the original graph by binary tag. So if that particular solution is in the solution of spanning tree, it's going to get a tag of 1. And if it's not in the solution of the spanning tree, then it's going to be a tag of 0, okay? So you can also add some additional edge features into your original graph, saying that whether this particular, just binary tag, whether this particular edge is present in the spanning tree or not. So now you are actually changing your original graph to something different, right? So you have the original graph structure, but you also have additional node feature and add feature. The node feature tells you whether this particular node is being selected as the solution in a particular spanning tree approximation. And the edge feature is going to tell you whether the particular edge is present in the spanning tree or not. So this is some scheme you can imagine you can augment your graph. Of course, spanning tree is just one way to approximate the graph. Depending on the type of combinatorial optimization problem you want to solve, you're going to actually augment it with potential different type of trees, right? Or different type of spanning trees. You can imagine that you can take your original graph and approximate it with multiple different spanning trees or multiple different type of trees, okay? Maybe maximum, minimum spanning tree, maybe low stretch spanning tree, things like this. And you obtain cheap solutions. You obtain the solution of that combinatorial optimization problem in this approximating structure. Typically, these solutions in this approximating structure is going to be in linear time, very, very efficient. Once you obtain this sort of solution in this approximating structure, you're going to add tags, a vector of binary kind of value tags to your node feature and add feature. So once you have this augmentation, then you can define a graph neural net policy on top of this augmented graph structure. So the overall kind of picture is like this. You have your original graph, and you have these solution which are, for instance, the darker node is going to be the solution present in a particular approximating structure. And then you can have several versions of spanning trees, tree approximation, and the solution of it. And you can even run some different version of greedy algorithms in your original kind of graph. And you can also use that to augment your original graph. So after you finish augmentation, then you get this graph neural net, in some sense, rich in features, right? Including features of the node, features of the edges. Then you define a graph neural net kind of policy on top of this augmented graph. And the learning will be the same as what we have seen earlier, either reinforcement learning or you can even use supervised and unsupervised learning nowadays to learn this graph neural net-based policy for solving combinatorial optimization problem. So actually, the idea is actually very simple. So you try to use some very cheap and simple approximation of the original graph, right? Some simple structure to approximate the original graph. So you might have seen this in variational inference as well, when you're trying to do inference in a very highly connected kind of a graph, grid graph. You can approximate it with tree structure, or even use a mixture of tree, like a weighted BP, to approximate it. And you solve your, original problem in this approximating structure, and then use the solution in this approximating structure to augment your graph. And then you run more kind of sophisticated graph neural approach, trying to actually discover or search for a more expressive algorithm to solve the combinatorial optimization problem. What we find is these features, based on cheap solution, cheap global solution for approximating structure, is very effective features. People have explored other ways to augment actually the graph before they apply graph neural net on top. For instance, you can actually augment each one of the node with some kind of random feature, or you can augment each one node with some identity one-hot feature, or you can actually use something more sophisticated, something called port number, a solution of weak to coloring problem in the graph to augment the node feature and edge feature. So what you will find that this feature we introduced based on spanning tree solution, and then to augment the graph, is an ingredient kind of solution to augment the graph is going to be much more effective. So in this particular minimal versus cover problem, we look at the approximation ratio for those graph neural net-based policies learned with a specific type of features. And this DAD approach, a differentiable algorithm search approach, based on this cheap solution to some kind of approximating structure, is giving you some algorithms which have much have approximation ratio much closer to 1. So the closer the algorithm to 1, the approximation, the better. Okay. So other features such as random feature one-hot and this port numbering and base approach will give you algorithm which is having higher approximation ratio. So this figure essentially shows you that this new type of augmentation approach is able to actually allows you to find potentially more expressive algorithms, and the learned algorithm is going to have lower approximation ratio. Okay. We have also compared this type of augmentation approach and the neural net-based approach learned on top of this augmented graph with some of these expert design algorithms, such as the two approximation algorithm we mentioned, and also some of the, for instance, LP relaxation for solving combinatorial optimization problem, and even for STP relaxation. So this graph neural net-based approach, based on our way of augmenting the graph, there are two versions. One is supervised learning, the other one is unsupervised learning. Both are producing, graph algorithms which has smaller approximation ratio. So all these hand-designed two approximation algorithm and LP-based relaxation and log n approximation is actually giving you a higher approximation ratio. So these algorithms, expert design algorithm, is not, in some sense, chained in the family of problem instances. We used to chain, we used to test these algorithms. But the graph neural net-based approach is able to leverage some characteristics of the distribution and learn some kind of graph algorithms which perform particularly well in that family of random graphs. In this case, is arabasi Albert kind of random graph. Okay. So far so good, and you use graph neural net to parameterize these, graph algorithms, and you can also make it more expressive by augmenting the original graph with some kind of cheap global features, and that gives you, some differentiable algorithm, learnable algorithm, yet expressive enough. So since I've shown you earlier based on the animation and also this kind of approximation ratio, you're able to actually find such and attain some kind of better performing algorithm. The question is, can we understand, why is it better, and then what makes these learned algorithms perform better, or which feature of the graph give you the decision, give this learned algorithm the decision that I should select this node but not the other node. Yeah, what is the structure around a particular node which tells you that this node should be selected? So we want to, in some sense, open up these graph neural net decision a little bit, the black box a little bit, try to understand, what is the local structure or what is the augmented feature which allows this graph neural learn policy to make a decision that I should select this particular node. So we actually trying to design some explainable model, trying to explain the decision made by this learned graph neural based algorithm. So essentially, for instance, your algorithm decide the probability of selecting this particular node is 0.3, okay, based on graph neural net based approach. And then what we expect the explainable kind of model to do is to given this particular node I and also the graph around it, we want to, this explainer model to be able to produce something like this, okay? Explain some kind of indicator saying that, okay, it is this particular edge around this node I, and it is this particular feature which is augmenting to that particular node, which helps us to make a decision that this node should be selected with the probability 0.3, okay? So in order to do that, actually, what we are doing is we are actually using a separate graph neural net to produce some selection, okay, probability for these edges to produce this explanation of whether this particular edge of node or feature should be selected. So essentially, what the sort of the explainer model is going to be, again, looking at a graph, around the particular node, right? Trying to see which one the edge or neighbor or the augmented feature are useful to explain that particular decision of selecting node I. And given this neighborhood around this particular I, you're actually going to also use graph neural net produce embedding. And this graph neural net is going to define the probability for instance, selecting a particular node as the explainer, okay? Or selecting a particular set of edges as the explainer, or selecting a particular set of features as the explainer. And then you're going to actually choose the top K of these explainer outputs and use it as explanation for the graph neural decision made in this learned algorithm. So the process actually can be this explainer architecture, the parameter also need to be learned, can be actually learned while minimizing the decision made by selecting this particular substructure, and before and after the selection, you can do it by minimizing the maximizing the mutual information between these two. Okay, so I'm not going to go into the detail, but you can think about explainable model which are defined in graph neural nets. Okay, and the explainer model itself is going to be a graph neural net. Okay, so then we can actually apply this explainer model to some of the algorithm we learned. For instance, we find that in this case, we try to use the explainer model to explain the decision of this algorithm learned for minimum word discover problem. So we are limiting, for instance, for instance, we try to explain this center node here, why it is being selected as the one node in the solution set. So we are going to explain, or limit the number of explainer component to be 5 nodes and 10 edges. So what's interesting, around the neighborhood of this particular node, what's interesting is this explainer network is able to select all these edges, which are directly connected to the center node. So it's like we already know that this greedy node algorithm, just looking at the node of algorithm is important. And this explainer seems to be able to actually, or the learning algorithm seems to be able to discover that the explainer is able to actually pinpoint that actually all these edges around this particular node, which contributed to, counting the number of neighbors or defining the degree of node is important for making that decision. So this is one example. This is another example. There are all these edges around this particular selected as explainer. Okay, so that's interesting. It seems that the learned algorithm is pretty much recovering the greedy kind of algorithm, and the explainer is able to actually pinpoint that as well. So another interesting thing we find that is since we can actually use this explainer model to explain the decision for each one is node, and we are limiting the the number of component for the explanation to be 5 nodes in the neighborhood and 10 edges in the neighborhood. So actually, we find that some of the nodes are frequently selected as the explainer node for other nodes. For instance, this particular node here with a dark color, it has been frequently selected as the explainer node for other nodes in the graph. So it's like some kind of anchor node. The decision whether we should select the other node as a solution set depends a lot on the presence of such a node. So this is like some kind of landmark in the network. Somehow based on landmark, you can look at the, or judge the importance of other nodes. So such a discovering of such a landmark node is also interesting because in the designs of GNN, there are some other work which actually try to specifically incorporate some landmark node to improve the expressive power or the quality of the solution graph neural nets. This explainer and the learning algorithm we have seems to be able to recover the kind of landmark node, which has already been found to be useful for improve these expressive powers of the graph neural nets. This is the sort of the, so here we can also explain which one of these augmented features are important. For instance, whether these solution for some of the tree, spanning tree are important or the greedy solution are important. Using this explainer model, you can also identify for the particular type of problem, what kind of augmented feature are more important than the others. For instance, if more meaningless card, we have augmented with a different type of node and edge greedy solution, and the tree dynamic programming, weak to coloring, and random feature. What we find is node greedy is much more important than edge greedy. So it's which kind of augmented feature are important depends on the type of problem. So it's going to be different for different problem. And this explainer model is able to pick out and tell you that what kind of feature important. So far, I've been talking about using graph neural net to define this sequential algorithm and learn with reinforcement learning, and then and also how to make this graph neural net more expressive, capture global information by augmenting the graph structure with some kind of cheap global feature. And the third component I've been talking about is essentially, once you have learned the graph neural net algorithm, you can actually deploy some of the explainable model on graph neural nets and try to explain which structure component is contributing to the learned decision in graph neural nets. And but the overall picture you can think about is something like this, right? In order to learn combinatorial optimization algorithm of graphs, you have several different aspects. You need to think about how do you design your search space, right? How do you actually learn it, right? That's what I mentioned by Arrow. And once you learn it, can you open up these black box, understand what kind of decision is made? So overall, the sort of differentiable framework for learning combinatorial optimization consists of this component. So we have been exploring some aspect of each one of these component, but there are many other things you can actually explore in each one's component, especially nowadays when we're looking at this combinatorial optimization problem, we are trying to, in some sense, solve a family of problems. There's lots of kind of opportunity out there. You can actually use learning to improve and potentially find some algorithms which are more effective than traditional design. With that, I'd like to finish the talk. If you have any question, you can just ask.
Yeah, actually, I think Pradeep has a question, but he had to leave a little bit earlier in the chat, and I missed it. So yeah, the question from Pradeep is, suppose we learn optimal policy for some specific graph problem. Can we then use it for a slightly different graph or problem? If not, then shouldn't we also add the cost of learning the optimal policy to the cost of running the policy itself?
All right. Yeah, thanks for the question. The first part of the question is, can we use it for a slightly different graph problem? Um, I can interpret it in two ways. One way is your input instance is different, right? So we hope by learning, you can use the graph neural nets, learning one graph and generalize to another graph. Yeah, as long as some of the characteristic the graph is similar, for instance, all scale free, although the topology are not exactly the same, hopefully the learning algorithm can capture some of the statistics in the graph and generalize to a different graph. That part that we actually have some experiments showing that you can do that. And the second kind of interpretation is different combinatorial optimization, right? Maybe you learn something for minimum discover, but you want to solve for maximum count. So this is an interesting question. People, I think, now that doing something related, it's more like pre-training, right, approach, yeah, for graph neural nets. So you want to learn some representation of the graph, maybe the node of the graph, such that it will be easier to learn other things on top of it. Maybe you can do something like, in this case as well, maybe you have a family of combinatorial optimization problem you want to solve, and some are more similar to the others, right? But those similar ones, maybe they're shared representation, which can help you solve, a new problem faster. You could set up some kind of maybe multitask learning or pre-training type of task to do it. We haven't done anything like that, but this question is very interesting. So the second part of the question is, if not, the cost of learning the upper parts to the. Yeah, that's. I imagine that the both questions in the first part can be done to settings that. Okay.
Yeah. So following on that, I think just like the pre-training is a very interesting idea because if you think of the graph embedding, it kind of feels like also like this word embeddings, right? Like they could potentially translate across a little bit of the different problems.
Yeah, right. So people have tried this pre-training or self-contrastive training graph neural net, mostly for classification problems, either node classification or edge classification problems. And then I haven't seen it done for combinatorial optimization problem. It will be interesting to see whether it can actually be helpful, yeah, or maybe whether there's any theoretical kind of justification that different combinatorial optimization problem they could share some features and help you solve all of them faster. It will be very interesting.
Right. Okay. Anyone else have any question for Le?
Sorry, I was kind of wondering, when you choose the global features from the spanning trees, I was wondering how you make sure later at inference the features are ordered, because for different graphs you have different spanning tree solutions, right?
Yeah.
So how do you make sure that at inference time, when you have a different graph, the features are actually you input if your GNN is actually ordered in a specific way?
Right. So here, the for instance, spanning tree 1 to n, it's mainly referring to different type of spanning tree, right?
Different.
Yeah. And then, for instance, for the first dimension of this node feature augment, it's the first type of spanning tree. And then the nth dimension of the augmenting feature is the nth type of spanning tree. So you, in something ordered that way. And graph neural net is inductive model, and it can just take these different dimensions and merge them with the graph structure and produce you the embedding. In some sense, it's ordered.
Okay. Thank you.
Any other questions, comments? I actually have a question. So I think in general, this whole process of using neural networks for this differentiable algorithm means that we need to come up with different graphs. But in general, how easy it is to come up with training graphs? Like, do you just randomly generate them, or like and how in terms of the amount, just how many of these graphs can there be when you have? I think you're dealing with nodes on the scale of like I believe from the bar charts like 200-ish, 300-ish.
Yeah, 100. Right.
Okay, but like what's the size of the data set that we're talking about here eventually?
Right. So actually nowadays people are able to train this graph neural net-based algorithm using unsupervised approach. There actually you can train with much larger graph and more graph. For instance, you can imagine if you have a graph thousands or tens of thousands of nodes, right? And if you use supervised learning approach, what I mean is you actually use some expensive solver to actually obtain some high quality solution of the graph instance, and then trying to use the solution as a supervision to train graph neural net. So that kind of approach can only scale to maybe thousands of them, depending on the difficult level of the graph. But nowadays, people have developed an approach which is unsupervised in some sense. You don't need to obtain this high quality solution, but you use the original objective function of combinatorial optimization problem constraints, and you can optimize your graph neural net policy using something more like an augmented kind of Lagrange approach. There, you can actually scale to larger graph, and you can use stochastic gradient descent type of thing to train with many graph instances as well. And yeah, so it's hard the training process, but it's improving in some sense. Right? So also you have another part of the question is what kind of graph you generate to train your graph algorithm. We have been experimenting it with some of the popular kind of model for graph. One is a random graph model, right? Random graph. The other one is this type of arabasi kind of graph, which gives you scale-free degree distribution, which is common in many social networks. So another very interesting question related to this is, of course, currently, if you train with that particular graph generator and test it on the new instance, also generated from the same graph instance, typically you find their performance is quite good. Even the size of graph increases, you can still find they generalize quite well, and the performance degrade gracefully in some sense. But another interesting question is, can we do something like a domain shift kind of, or transfer learning type of thing, right? Suppose your training graph distribution is something like this. Can you actually design some optimization procedure or something such that if you learn on these type of distribution, you can even obtain generalization guarantee or good performance in slightly shift the kind of distribution. So maybe some of these optimization techniques handling robust optimization, optimization under adversarial kind of attack or something could be used in this case and help you train a better graph neural net algorithm, which can perform well even in some bad, hard instances, which is slightly different from the typical instances you sample from your distribution. Right? Yeah, so it's I haven't seen anything like that yet, but it seems to be very interesting. Right? Yeah, question. You're muted. Yeah.
Sorry. And do you have a sense of how bad the scale could affect the complexity of the problem that we're solving here if we do this pipeline of spanning tree, RL, and then eventually right?
So you mean the spanning tree, some of the spanning tree is a low stress spanning tree. It can be attained in near linear time in the number of nodes and edges. And in theory, then this approximation step using spanning tree, and then obtain chips, solution for this tree approximation is going to be efficient, right? Even for very large graph, right? And then, but the sort of the bottleneck or slow part is still going to be in, running the propagation for the message pattern for this graph neural net and optimizing the pyramidal graph neural nets, right?
Okay, right.
Right, yeah.
Okay, yeah, thank you. I think we're a little bit over time already. Does anyone have any other question that they would like to ask? Okay, cool.
All right.
Well, let's thank Lil again for this amazing talk. I know it's pretty late in UAE already. It's like 10 p.m., I think.
Mm.
So yeah, thanks for staying up late with us. Well, as a reminder,
Okay.
we're meeting again next week. And well, thank everyone, especially Lil, for attending the seminar today. And if anyone's interested, definitely follow up with later via email to ask questions as well. Well, thank you, everyone.
Great. Yeah, thank you everyone for coming. Yeah, feel free to send me email if you have further questions.
Yeah.
Okay, great. Thanks for
All right,
organizing.
thank you. Stay safe.
See you then.
Bye-bye.
Bye.